So this is what the exact entry. Actually, this is what the interpretation that makes diagonal entries as like variance of each features and off diagonal entries as like pairwise covariance. Difference, actually this matrix rotates points while preserving their length. Okay, and here kindly just observe difference. This one we have a standard counterclockwise rotation, where that exact standard counterclockwise rotation, it just shows here it is cos theta minus sin theta, and to the second row it would be the sin theta and cos theta. So actually this code flips the sign of the sine term to rotate in the opposite direction. Kindly have a note on towards this. And here, kindly just note a difference about this sigma. It is slightly different from the standard one. What is the exact standard one is e to the power of, that is raised x square plus y square divided by 2 sigma the square. Actually, this is what the standard one, and here we have slightly differed from the standard to make it radially symmetric Gaussian-like function. Scale dependent relationship where larger magnitude values for higher variance features. And when on just going with the correlation matrix, so that is normalized version, that is skill invariant, kindly observe, and clearly structured. Clearly structured, yes, here this is what the orthogonality. And yes, when on just specifying the determinant of that t, which is equal to 1, yes, this specifies the rotation, not a reflection. And here kindly just observe the vertical line of points is rotated 36 degree. Okay, so 36 degree clockwise without any stretching. Every point maintains its distance from the exact origin. Okay, so this exact gradient magnitude, let I just specify it mathematically. So actually it is a square root of horizontal edge the whole square plus vertical edges the whole square. So horizontal edges, yes, it is dou I by dou x the whole square plus dou I by dou y the whole square. So this is what the mathematical interpretation. So it just combines directional derivatives into a rotation invariant edge strength. Happy morning, dear friends. Here's yours, Dr. Rajanta. Welcome to Demystify with Ajay. Dear friends, previously we have discussed about the theoretical machinery of matrices. And this session puts that machinery to work on 3 applications that are central to data science or machine learning or deep learning, generative AI, mainly on computer graphics. So let me just start with covariant matrix. Dear friends, covariant matrices represented as X transpose multiple by X. So these matrices help us understand the relationship and correlation between different features in the data. Next, we are going to discuss on geometric transformation. Yes, these include operations such as translation, rotation, scaling, and flipping, allowing images to be viewed from different perspectives while preserving meaningful information. Finally, image filtering. This is the core operation in computer vision, where a kernel or filter slides across an image to extract important features such as edges, textures, and patterns. And before that, let we include our important necessary libraries. And here we just go, dear friends, we have already discussed this in our previous sessions also. Yes, the NumPy for mathematical, so numerical Python, Matplotlib for plotting. Yes, we have already discussed about those warnings and those default parameters. And dear friends, we have just included that random seed. So this fixes the random number generate states which ensure reproducibility. And yes, let me just execute and let me check what is the version of NumPy. Yes, it is 2.3.5. Okay, so we are just going to start with the multivariant data covariance matrix. Yes, starting with from bivariant to multivariate. Dear friends, previously we have computed the Pearson correlations between two variables using the dot product of mean centered vector normalized by their norms. With p variables, we all need pairwise correlation. And kindly just observe, dear friends, when we just specify the pairwise correlation, yes, it would always be as a P into P matrix. Rather than looping over pairs, matrix multiplication computes everything at once. And yes, covariance is the unnormalized version of correlation. So the dot product of mean centered variable would be divided by n minus 1. Kindly just keep it in mind. And here we just go with the equation. Observe, dear friends. So here covariance between variable a and b equals 1 divided by n minus 1 multiplied by the sum of from I equals 1 to n of x sub I minus x bar multiplied by y sub I minus y bar. Okay, here it equals 1 divided by n minus 1 multiplied by x tilde transpose multiplied by x tilde. So here kindly just observe, dear friends, where x tilde, which is equal to x minus x bar, is the mean centered variable. And yes, dear friends, when we just pack all p variables as a column of an n into p matrix x. So here mean center each column to get x tilde, and yes, we just get the exact equation as I have already specified. Yes, C equal 1 divided by n minus 1 multiplied by x tilde transpose multiplied by x tilde. So this equation computes all pairwise covariance among variables simultaneously. Here actually, dear friends, element we are just specifying I or whatever be the j is exactly, yes, that is x tilde transpose multiplied by x tilde, which is the covariance numerator. And here the result is always symmetric. Symmetric is in the sense, yes, of course, here we can just say C A comma B, which is equal to C B comma A. And when we just speak on towards, yeah, so this is what the symmetric. And when just we speak about this square matrix, of course, here we just took P into P matrix, because we already discussed about that is A transpose A is always a square symmetric. So we have already discussed previously. Okay, now let me just discuss about this multivariate, okay, multivariate data set with known structure using code. So here we are just starting with, of course, anyhow, we have just already previously included about this random.seed. Okay, so this fixes that random number generator stator as 42 and ensures reproducibility, that is every execution produces identical data. And we have just given the dimension, the data set dimension as n is equal to 500 observations. So here number of samples is there, and p is equal to 6. Yes, these are the number of variables. And when we just go for this latent variable, yes, this is what hidden factor. So we have two independent standard normal form, Z1 and Z2. So these act as latent factor that induce correlations among observed feature. Actually, conceptually, they represent hidden source influencing multiple variable. And dear friends, here we have an X, that is the features with controlled correlation. Each feature is constructed as like, kindly just observe. So here it would be as like a feature which is equal to loading into latent factor and plus noise. And dear friends, kindly just observe here we have already specified that is x0. This strongly depends on Z1 with small noise. So here high correlations with Z1. Okay, and next it is x1. Yes, moderately depends on z1. So I am just specifying this moderately or highly by using this constant variable. Okay, so here it is still correlated but noisier. Next, we are just going to have x2. Actually, it is an negatively dependent on this z1. Negatively dependent on z1. So here it is correlated with x0 and x1. And next, X3, yes, it is strongly dependent on Z2 and correlated with the X4. Next, moderately dependent on Z2. Yes, that is what the X4. And last but not least, X5. Yes, it is the pure noise that is independent of all others. Dear friends, this construction produced two correlated feature groups. Yes, of course. Let I just give you one thing. So here, this group 1, yes, it is Z1, which is driven with X0, X1 and X2. And this is strong internal correlation. And here, X2, it is negatively correlated with X0 and X1. And the group 2, yes, it is Z2 driven, and here we have X3 and X4. So both are positively correlated with each other. And last but not least, yes, the noise feature X5. So no systematic correlation with any feature. So these resembles a factor model with two latent dimension. And dear friends, kindly just observe here we have just specified the feature names. Yes, these are labels formatted by latex cell rendering, and actually it is for plotting. Okay, so next let me just have the exact output. Okay, so the output statement that is confirms the shape of the data set. And let me just execute and I see what is the output. Yes, kindly just observe, dear friends. Here we have, yes, 500 comma 6. That is, we have 500 observation with 6 features. So this one we have created 500 into 6 data matrix where feature x0, x1, x2 shares a common latent factor z1 with x2 loading negatively. And here feature x3, x4 shares z2 and x5 is pure noise. So the covariance matrix should reveal these block structure. And dear friends, I just add one more thing. So dear friends, when we just have this code simulates actually this data following a linear latent factor model. That is x, which is equal to zw plus epsilon. So here this exact z, yes, these have two latent variables z1 and z2. Of course, we have already discussed this. And yes, this W, which it just specify as feature loading. And here we have the Gaussian noise. And dear friends, yes, to test PCA or validate factor analysis methods. And of course, it is used, commonly used to benchmark clustering or dimensionality reduction algorithm. So kindly keep it in mind. Okay, now let me just discuss about computing the covariance matrix from first principle. Let me just start with defining this column means. Dear friends, actually this computes the mean of each feature, that is column wise. And of course, we have already seen, that is we have the feature 6. So yes, it just results the shape with 6. And exactly this corresponds to the equation. Of course, we have already seen that is mean j, which is equal to 1 by n, summation of I, which is equal to 1 to n, x sub ij. So this is what exactly, this is what to corresponds to this column wise centering the step. Next, let we just move on to define this x style. Yes, this is what the mean centered data. Actually, there's x style which is equal to subtract the column means for every row wise using broadcasting. And of course, we have already know the shape. Yes, it is 500 comma 6, yet it is just going to remains the same. And mathematically, we can just express it as like, yes, x sub ij tile, which is equal to x sub ij minus mean j. So this ensures each column has zero mean, which is required for covariance computation. Okay, now next let me just define the manual covariance matrix, which is equal to, see, actually this was the exact equation which we have already discussed. Yes, so here the C manual, which is equal to C equals 1 by n minus 1, okay, x style transpose multiple by x style. So that is what given here. Okay, so dear friends, actually this is the exact standard sample covariance formula, and here we have already know this x tilde is exactly 500 comma 6 we have already seen, but here it is specified as like t, that is transpose. So here it would be as like 6 comma 500. Okay, so multiplied with x tilde, so multiplied with 500 comma 6. Okay, so it is divided by n minus 1. So here the results, it would be 6 comma 6. And for each entry, how this would be calculated? So this would be calculated as like, okay, so here CJK, let I just specify like this. Okay, so 1 by n minus 1 summation of I, which is equal to 1 to n, and here x sub ij minus mean j into x sub ik minus mean k. So this is what the exact entry. Actually, this is what the interpretation that makes diagonal entries as like variance of each features, and off diagonal entries as like pairwise covariance. Okay, so yes, dear friends, now let me just go with the NumPy covariance here. Okay, so this is what the covariance calculated using NumPy. So this computes covariance using NumPy implementation COV. Okay, and here we have just specified as row variance, which is equal to false. Yes, this indicates that columns are variables, that is the features. And here also uses normalization by n minus 1 by default. Okay, so let me just see the exact resultant by providing this output, that is shape and value here. Here it is the shape and value, so it just displays the covariant matrix rounded to 3 decimals. Okay, and here this one, yes, it just verifies numerical equivalence between manual and NumPy results. So if it is both match, it just expected result would be true. Let me check. And yes, the next one the same by using symmetric. And here it just conforms the matrix in symmetric. So we have already seen what is the symmetric is. Anyhow, I just let you know it is C sub jk, which is equal to C sub kj. Okay, so let me just see this whether it is matching or not. So we're expecting a true value. And next we are just going to have the variance, that is the diagonal factors. Okay, so this extracts the variance of each feature. Actually, dear friends, these reflects higher variance for features with stronger latent signal and inclusion of noise. And here this independent noise feature x5, of course, should have variance which is equal to 1. Okay, so let me just see how this is happening, and let I execute. So kindly just see here, we have the covariance matrix 6 by 6. Okay, so this is what 6 by 6 symmetric, and computed as we have already know, we have 500 observations. So in such case, it would be as like 1 by, that is n minus 1. So here 1 by 499, and yes, x style transpose multiple by x style. Okay, so it matches towards this exact covariance while using this NumPy. Okay, to machine precision. And here this diagonal contains the variance of each features. So this is what the exact diagonal that contains the exact features and the covariance of a variable with itself. And the off diagonal, other than the diagonal elements, are the pairwise covariance. And here I just want to specify one thing. Usually some would ask why this n minus 1. Actually, this is Bessel's corrections. I just specify. Yes, this is Bessel's correction. See, actually dividing by n minus 1 instead of n gives an unbiased estimator. So mainly for population covariance when working with a sample. So that is what we are using here n-1. So kindly just keep it in mind. Anyhow, I just added with that. Okay, and dear friends, of course, by using this code, yes, we have seen, yes, how covariance arises from mean-centered interproducts. And yeah, we have just seen both are matching, both are symmetry, and this is the exact diagonal variance also. So this equivalence between, yes, linear algebra formulation and library implementation. And of course, I just add up with this the key properties of this covariance matrix. Yes, mainly it is of symmetry. And second one, yeah, we have just seen about the variance on this diagonal. And last but not least, yeah, structured correlation from latent variables. Okay, now let me visualize and numerical representation of this covariance and correlation structure of this data set X. Okay, and dear friends, this is what the figure comma axis. Yes, this creates figures with two subplots side by side. Yes, that is what subplot 1 comma 2. So here let me just have one on covariance matrix plot and another correlation matrix plot. Okay, so here let me just go with this covariance matrix. So yes, dear friends, here we have axis 0, and we have just specified np.max, that is numpy.max, and here I just defined this im. See, actually this displays the covariant matrix as a heat map. Okay, and dear friends, kindly just observe this one here. We have just specified color map as like red, blue, positive correlations and negative correlations correspondingly. And here I have just specified this V min, which is equal to minus V max, and V max, which is equal to V max. That is ensures a symmetric color scale around 0. Okay, so this is to know about the exact plotting. So I just want to set up this before making the execution. So I have just given this, and next it is all about the color bar. Of course, it adds a legend for interpreting color intensity. And next we just gone towards the axis labels. Okay, so yes, labels rows and columns with features as like x0 to x5. That is also we have just seen. And yes, of course, we are going to have it within a loop. That is, this writes numerical covariance value inside each cell. And of course, we have just given the text color, so that adapts for contrast. So here white text for strong value, and black text for weak. And next we have just included the title. Okay, so this is the exact title of that plot. Okay, we are moving on to this correlation matrix. So kindly just observe, dear friends, here we have, that is actually, we have defined the standard deviation. Just defined this R manual, yes, which is just a specified matrix of all pairs of sigma 1, comma sigma change. Okay, so let I just specify by using an equation. Kindly just observe, dear friends, it is R sub ij, which is equal to C sub ij divided by sigma I multiple by sigma j. So actually the correlation between variables I and j equals their covariance divided by the product of their standard deviation. That is what it is specified. Okay, so here we are just going to calculate it by using this one. And of course, dear friends, this one correlation coefficient, yes, this is built in Pearson correlation computation, which we just implement by using this numpy. And next here correlation matrix visualization. So I have just given this one. So kindly just see here V min, which is equal to -1. So perfect negative correlation. And this one V max, which is 1. So here it is for perfect positive correlation. And of course we have included the correlation color bar also. Okay, and next we have included the labels for exactly as I have already specified, and this is the exact loop. Yes, it just highlights the moderate to strong correlation. So hydride to strong correlation is in the sense, yes. So here it would be as like the P which is greater than 0.5. Okay, and last but not least, here I have just specified the title. Okay, so let me just visualize the final layout. Okay, and here we are just going to have our tight layout because to prevent overlap of labels and plots. Okay, and last but not least, let me just save the visualization as an image file, and let me execute and display the image. So kindly just observe, dear friends, the block structure, of course, is exactly what we designed. This upper left 3 into 3 matrix block, that is what x0, x1, x2 shows the z factor. And here x0 and x1 are positively correlated while x2 is negatively correlated with both. Now the center block x3 and x4 shows the z2 factor. And here the x5, yes, has a near zero covariance with all other features, that is independent noise. And this cross block entries, that is example from x0 to x3 or near zero, which is the exact two factors or independently. And here when we just discuss about this interpretation within this covariance and correlation, kindly just see here, dear friends, this dividing each element by the product of the feature standard deviation normalization to -1 to +1 scale. So that is what here it is. Each and every value that is between -1 to +1. So this it would specify as like which we just say here. Yes, R sub ij which is equal to C sub ij divided by sigma I multiple by sigma j. So in mathematical notation, it is specified as like, kindly just observe here, dear friends. This is R which is equals to D inverse multiple by C multiple by D inverse. So here D is the diagonal matrix containing standard deviation. Kindly just observe this one. And when we just say towards the D, kindly just observe this is the diagonal matrix of sigma 2 till sigma p. Okay, so the correlation matrix always has ones on the diagonal. So here we have, once again, I just show you. So yes, that is what here in diagonal we have all ones. And dear friends, this covariant matrix appears everywhere as the core of PCA and in Gaussian mixture model also. So in portfolio risk analysis and in Kalman filters also. Okay, so here kindly just observe here with this covariant matrix, it just reflects the scale dependent relationship where larger magnitude values for higher variance features. And when on just going with the correlation matrix, so that is normalized version, that is skill invariant, kindly observe, and clearly structured. Clearly structured, yes, here it as so here it is as like x0 and x1 as positive correlated, and of course x3 and x4 also positively correlated, and when on just taking towards a strongly negative correlation as like x2 versus x0 and x1. And one thing, nearing zero correlation is also there, where between x0, x1 and x2 and to x3 and x4. So any feature with x5, that is also it is nearing zero correlation. And dear friends, this code demonstrates how to visualize covariance versus correlation. So here, why we have just correlation, often we are just preferring correlation is, yes, it comparably across features and it is bounded. Kindly observe the value, it is already bounded within -1 to 1. And here, of course, it is mainly important how latent structures appears as block patterns in this heat map. Next, we are going to discuss on geometric transformation. Yes, these includes operations such as translation, rotation, scaling, and flipping, allowing images to be viewed from different perspectives while preserving meaningful information. Okay, dear friends, this code constructs and visualizes a 2D rotation transformation. So verifies its mathematical properties and demonstrates its geometric effect on a set of points. Okay, before going to coding, I just want to specify one thing, dear friends. Dear friends, actually, this matrix has two remarkable properties. Yes, one is columns are orthogonal. So kindly just see here, cos theta multiple by sin theta plus minus sin theta into cos theta, which is equal to 0. So this is what specified as columns are orthogonal. And the second property, yes, of course, columns are unit vector. It would be just specified as like an Pythagorean identity. What is it? Yes, of course, cos square theta plus sin square theta, which is equal to 1. So a matrix with this orthogonal unit norm is called as orthogonal matrix. An orthogonal matrix, if it satisfies T transpose multiple by T, which is equal to 1, which means, yes, of course, T inverse, which is equal to T transpose. So let me just see what the exact code defines. So dear friends, actually here, this theta, which is equal to np dot pi divided by 5. So actually this is what the degree clockwise, that is 36-degree clockwise. And here we have the matrix, that is the exact T matrix, T of theta, which is equals to a matrix whose first row is cos theta, sin theta, and the second row is negative sin theta, cos theta. Difference, actually this matrix rotates points while preserving their length. Okay, and here kindly just observe, dear friends, this one we have a standard counterclockwise rotation, where that exact standard counterclockwise rotation, it just shows here it is cos theta minus sin theta, and to the second row it would be the sin theta and cos theta. So actually this code flips the sign of the sine term to rotate in the opposite direction. Kindly have a note on towards this. Okay, so this is what, and here this would be the 2D rotation. Okay, and here this what makes the opposite side of the rotation. Okay, yes, let me just move on to the next line of the coding. Yes, here it just shows the exact numerical verification of the property, that is orthogonality. Okay, now let me just verify the orthogonality property by using exact equation that we have already discussed. Yes, T transpose, okay, matrix T transpose multiple by T, which is equal to identity. That is the exact numerical verification of property, which is an orthogonality. Okay, so this exactly shows us like T transpose multiple by T, which is equal to the identity. Actually, this confirms columns are orthogonal. And yes, this implies, kindly just observe, the length would be preserved and the angle are preserved. And next, of course, kindly just observe, dear friends, here we have the numerical Python, that is NumPy functionalities. This it just shows the determinant. Yes, for the property of rotation, we are just going to have as like determinant of T, which is equal to 1. And here, kindly just see here, dear friends, if this interpretation is a positive one, yes, it's just a rotation but no reflection. But if it is a negative one, of course, it just makes the reflection. So this is rotation, and this negative one, it would be the reflection. Okay, now let me just move on to the next line. Yes, this exact construct the input geometry. Okay, so here, of course, kindly just observe, we have a vertical line of points, and this shows the exact one, and this generate 8 points along the y-axis. So along the y-axis here, it would be as like, so kindly just observe, it would be like 0, comma yi. So yes, it has the shape of points would be 2, comma 8. Okay, next let me just apply the exact rotation. Dear friends, this matrix multiplication rotates all points simultaneously. So each column is transformed. Each column is transformed how? Yes, exactly. So the x rotation which is equal to t times x. Now let me just visualize the plot originally and rotate points also. Okay, so that is what here it is given, and kindly just observe the original. Yes, it is in black circle, and towards the rotated, yes, it's in blue. That is what it is specified, and here we have that blue, and kindly just see here, this would results with an line becomes a tilted line that is rotated clockwise in 36 degrees. So that is what here we have specified. Okay, and next one, kindly just observe, dear friends, we are just having a rotation arc annotation. Okay, an arc annotation, yes, it just draws a small arc indicating the rotation angle and starts at 90-degree vertical direction and moves clockwise. Okay, now let me just have our axis and styling. Yes, we have just specified just equal scaling ensures geometric accuracy, and axis lines emphasize the rotation about the horizon. And dear friends, yes, let me just have, this is the exact title, and we just shave the figure and saves this visualization. Let I execute and see what is the output. Okay, so kindly just observe here. So this is our T, and yeah, we have the orthogonality as T transpose multiple by tree, which is an identity. So that is what here it is specified. And with this resultant, yes, dear friends, so here what is just shows is the rotation matrix T with pi by 5, that is 36 degree, it just satisfies, that is T transpose dot T, which is equal to identity. This is what the orthogonality. And yes, when on just specifying the determinant of that t, which is equal to 1, yes, this specifies the rotation, not a reflection. And here kindly just observe the vertical line of points is rotated 36 degree. Okay, so 36 degree clockwise without any stretching. Every point maintains its distance from the exact horizon. And one thing I just want to specify here, dear friends, for counterclockwise, okay, actually the exact rotation here, it is specified as like a counterclockwise rotation where it just negate a theta, that is equivalently, and makes the transpose of the matrix. T matrix of minus theta, which is equal to T of theta, the whole transpose. So this is what it is specified as like counterclockwise. And dear friends, kindly just observe, dear friends, here the rotation property, whichever we just specified here, I just want to make you a simple point. Yes, first of all, according to the rotation property, the length is preserved. Yes, of course, the length is preserved by, yeah, the norm of matrix T of X, which is equal to the norm of x. So with this, the length is preserved, and of course the angle is preserved, but there is no distortion. Okay, so the no distortion is in the sense no, that is it is a rigid transformation. And when just coming towards the geometric effect, kindly just observe, dear friends, the second one we are just going to discuss on geometric effect. Yes, the original point lies on a vertical line. Of course, after transformation, yes, the line rotates according towards 36 degree. Okay, so the line rotates and the distance between each point, kindly observe, remains unchanged. And here orientation changes, but not the shape. The shape remains also the same. Okay, now next, it is all about a broader context. Dear friends, this is an example of an orthogonal transformation. What is it? Yes, of course, T inverse, which is equal to T transpose. So such transformation are fundamental in PCA, computer graphics, robotics, and coordinate transformation. So of course, it is also used in eigenvector based decomposition. Okay, now next, of course, kindly just observe, dear friends. We have just discussed a pure rotation matrix preserves length. Yes, of course, the same. And here, a general 2 into 2 transformation matrix can both rotate and stretch. Rotate and stretch. Yes, that is what specified as like the wobbly circle. And here towards the exact matrix, dear friends, it is specified as like, yes, T pi, which is equal to matrix with the first row as 1, 1 minus pi, and second row it is 0 and 1. And dear friends, the diagonal element scales the axis, both 1 here. Yes? So no scaling. But while the off diagonal, that is off diagonal, kindly just observe, it is 1 minus pi. So shears the x-axis based on the y coordinates. So here, if the pi which is equal to 1, of course, t would be 1. No transformation. And here, if this pi moves away from 1, yes, the circle also get sheared. So that is what shear transformation. Okay, now let me just discuss with the code. Yes, this exact code visualize a family of shear transformation applied to the unit circle and verifies a key algebraic property, that is determinant. Okay, so this result is the so-called wobbly circle. Let me just see, and of course this is an ellipse-like shape. Okay, yes, dear friends, kindly just see here this exact, let me just define the theta, and here we have an line space with 100 coordinates, okay, and yes, and here we have the circle, and which it just has a shape of 2 into 100, okay, and when on just making these two things, yes, this just gives us, kindly just observe here the parametric of representation of x, which is equal to cos theta, and y, of course, it defines the sine theta. Okay, so that is what here it is specified as like a theta, and here when coming towards the circle, yes, it has the shape of 2 into 100, where it just shows that is row 0, it would be the x coordinate, and the row 1, it would be the y coordinate. And dear friends, kindly just observe here, this is the exact parameterized Shearing transformation. Okay, so parameterized shear transformation, and here each value of pi defines a different transformation matrix. And that is specified here. So for each different values, we are just going to have this loop functionality, and yeah, this is what which I have already specified. So this is what the exact equation which has the general form as like which we have already discussed. Yes, T of pi equals a matrix with the first row as like 1 and 1 minus of pi, and second row as 0 and 1. Okay, now let me just move on the interpretation of the transformation. So here it is what applied. So transformed, which is equal to t at circle. So dear friends, actually this a point, for a point x comma y, the transformation would becomes as like so this exact equation would be just specified. So here whenever we have a point at x comma y, so this would be transformed as like x dash, which is equal to x plus 1 minus pi into y, and here y dash, it would be the same y. So what would just it resembles as like, yes dear friends, the y coordinates remains unchanged, but the x coordinate is shifted proportionally to the y. Okay, so this is a horizontal shear. That is what it shows. Okay, and I just want to give you a small information also. Kindly just have a note on towards, dear friends. If here let me have a pi and this is 1 minus pi, what happens when this is affected? Okay, so here in such a case, if the pi is 1 and to the 1 minus pi if it is 0, okay, so it is specified as like no shear would be done and it is as like a perfect circle. And if the same pi has a value of 0.5 and 1.5 also has the same value of 0.5, okay, a mild shear transformation occurs. And kindly just observe, if the pi is 0 and 1 minus pi is 1, so there would be a moderate shear would be applied. And here to the last it is minus 0.5 and here it is 1.5 under 1 minus pi. A strong shear transformation would appear. So kindly just observe this exact 1 minus pi, if it is increases, yes, the circle becomes increasingly tilted and stretched horizontally. So the shape resembles an ellipse skewed to the right. Okay, so let me just visualize that. Okay, and here kindly just observe the exact plot that transformed points as like scattered. Okay, so here let me just set the axis of fixed and equally scaled, and this ensures geometric distortions are accurately represented. And let me just have the title. Okay, so just displays the of course displays the parameter value and explicit matrix formation. And kindly just observe, let we have the one important functionality I have to specify here, dear friends. This one, it is to check the determinant whether the area is preserved or not. Okay, and for this what we are just going to have is we are just going to have a value of a, so that would gives you, kindly just observe, that would just show that is t which is equal to 1, a matrix of 1 and a as a first row and 0 and 1 as our second row, where this gives our determinant of t which is equal to 1. So let me just see what is the output here, and let me just go towards the visualization too. So here we just got the exact output. Kindly just observe, dear friends. As I have already said, yes, the pi 1, okay, and kindly just to see here, the t, determinant of t is also 1, and the circle is undistorted. As this pi value is getting decreases, the off diagonal element of this 0, that is 1 minus pi, introduce as shear. That is, the upper half of the circle is pushed to the right side, and the lower half is pushed to the left side. So our frame has a determinant of t which is equal to 1. That is meaning the area is preserved even though the shape changes. So the area of the circle, the area of this ellipse, of course, this is what the wobbly circle. Yes, the area is preserved, but the shape changes accordingly. So this is what shear transformation. So one of the fundamental transformation type. So with this, yes, dear friends, I have to specify one important aspect. So when on just executing this coding, yes, this exact codes gives us, yes, of course, it has an area preservation. That is determinant of t which is equal to 1. So area is unchanged. Even though the shape distorts, its area remains constant. And the next one, of course, it is a non-orthogonal transformation. Yes, unlike rotation, here the angle is not preserved. and the lengths are also not preserved. So the circle becomes a sheared ellipse-like figure. Okay, and next one, of course, kindly just observe, dear friends. The third one, it is all about linear transformation. So linear transformation, yes, of course, this is the unipotent matrix. So here we have the Aegean values as like lambda 1, which is equal to lambda 2, which is equal to 1. So no diagonalizable, that is in general. And yes, this represents a pure shear, not scaling or rotation. Okay, now let me just move on to a determinant as a area or volume scale factor. Difference, actually this exact code provides a geometric demonstration of a central linear algebra result. Actually, what is that? Yes, so kindly just observe determinant of matrix T, which is equal to area scaling factor of the transformation. So that is what's said to be central linear algebra result. So it visualizes has different 2 into 2 matrix that transforms a unit square and how their determinants relates to the resulting area. So that is what we are just going to visualize it. Okay, so kindly just observe, we are just going to have our plotting, and here we are just going to have 4 subplots, one per transformation. Okay, and what is that exact transformation? Yes, one is identity, and next one it is going to be a scaling of 2 types, and yes, a rotation, and last but not least, it is singular. Okay, and here let I just give you the exact transformation functionality. So if it is an identity, so exactly, so T it would be equal to 1, and here to the same determinant would also be there. And yes, dear friends, this is what's said to be no change in shape or area. The next one we just say, yes, it is going to be a uniform scaling. So what is uniform scaling is? Yes, exactly. So here T, it would be the 2 times of identity, and here our determinant would be 4. So here each axis doubles. Okay, so area it just becomes 2 into 2, which is equal to 4. And next we are just going to have the rotation. Okay, so next it is all about a rotation, and kindly just to see here we are having 45-degree rotation. So yes, so that 45-degree clockwise rotation. Okay, so here determinant it would be equal to 1. So pure rotation, shape preserved, and area also would be preserved. And last but not least, yes, we are just going to discuss about the singular matrix. So here singular matrix, of course, we have an array as like 1, 2 and 0.5 and 1. So here if I just compute the determinant for this, okay, so let I just have the first matrix here. So 1, 2 and 0.5, 1. Okay, so this is the matrix exactly. So if I just evaluate the determinant, which is equal to 1 into 1 minus 2 into 0.5. So which is equals to 1 into 1, that's sorry, 1 minus 1, so that is equals to 0. So this matrix is purely singular. So it collapses 2D space onto a line, that is 0 area. And dear friends, based on the unit square, okay, so based on this unit square, let me just have this one. So this defines a closed polygon, so that it returns to origin, that is area which is equal to 1. And net we just apply the transformation. What is the transformation? Of course, all these 4 inside a loop, let me just apply the transformation. And here this applies transformation for each vertex. Okay, and here once it is done, yes, it produces a new quadrilateral, that is degenerated shape also. And dear friends, this one is just going to visualization of logic functionalities, that is as like whether it is a gray color, and of course it is a light gray color, and we are just going to have a dashed border. Okay, so that is also here it is specified, and the exact transformed shape it would be as like blue and red. So here when just comes towards blue, yes, it is non-zero determinant, which is area preserved or scaled. And for red, of course, it just specify as like near zero determinant, that is area it is collapsed. Okay, and here we have the exact title, and which is just displays the transformation type and determinant. Okay, so let I just execute, and let we observe the result. And here we have, so this one it is identity. So yes, there is no change we have. Of course, area is also preserved. Okay, no changes there, area is preserved. And when coming towards the scaling, as 2 times scaling, okay, here our determinant, which is equal to 4. So each axis is doubled. So as I have already specified, yes, this is what here. Okay, so each one it is doubled. So we have 2 into 2, which is equal to 4 times larger. Okay, that is what we just got here. And the next one, rotation of 45 degree, rotation of 45 degree. And here, dear friends, the shape is rotated, area is preserved. So the rotation is volume preserving. That is also keep it in mind. Okay, the volume is, that is area is preserved. The shape is also that, but one and only the angle. Exactly, we have only the angle. So the shape may rotate but not distort area. And last but not the one, it is singular. So the square collapses into a line. So one dimension is completely flattened here. So this is what the determinant is equal to 0. So that is what here we have just discussed. So that is what it is specified as determinant is 0, means geometrically. So yes, dear friends, with this visualization, what we have just observed is, yeah, determinant as area multiplier. For any region, if I just specify any region as like A, so here it would be area of T of A, which is equal to, yes, absolute determinant of T multiplied by area of A. So this is what it's said to be determinant as area multiplier. Next, when on just going as with an sign of determinant, dear friends, if it is a positive, yes, it is a orientation preserved. And if it is a negative, of course, orientation, it is flipped. That is reflection happens. Okay, and next we have just discussed about shearing, of course, scaling, of course, we have just seen the rotation also. So here rotation, it just preserves area and shape. Okay, so area and shape it is preserved. And when coming towards scaling, changes, of course, area uniformly. And when coming towards this shear, yes, from the previous example, what we have just seen is, yeah, it just preserves the area but distorts the shape. And last but not the least, yeah, we have also discussed about the singular, which destroys the dimensionality itself. So yes, dear friends, of course, this exact code demonstrates that the determinant is not just an algebraic quantity. It has a direct geometric meaning, area scaling in 2D or volume scaling in higher dimension. And of course, here linear transformation can preserve area, scale area, collapse space, everything. Of course, these are the exact importance when we just visualize it. Okay, by this we are just able to see, yes, dear friends, this geometric transformation use matrix vector multiplication and mainly this transverse of this matrix vector multiplication to rotate or scale and shear coordinate. And here pure rotation matrix or orthogonal, that is also we have just discussed. Okay, and which just preserves the length. And dear friends, the determinant of the transformation matrix that gives the area or volume scale factor. And last but not least, determinant which is equal to 0 means the dimension is collapsed. And of course, we have also discussed about wobbly circle, demonstrated how parameterized transformation creates animation. Finally, my dear friends, in this session, we are just going to discuss about the image feature detection. Yes, it is what the important application, matrix application used mainly in computer graphics. And in this session, we are just going to discuss about 2D convolutional with Gaussian and edge detection kernels. Dear friends, we have already discussed about the filtered time series by sliding a one-dimensional kernel and computing dot products. And here, image filtering extend this to two-dimensional. This two-dimensional kernel slides across the image, and at each position, we compute a Hadamard product and make the summation. What is that Hadamard product? Yes, dear friends, kindly just to see here, output of row and column, output at row R and column C, that equals the double summation over I and J of K sub Ij multiplied by S sub R plus I, C plus J. Actually, this is what the exact one which we just specified, Hadamard product and the summation. And dear friends, this is nothing but a simple thing. Say, multiply the kernel, that is the kernel values, with the image patch value. Then add it. Then add everything together. That is the exact functionality. So, which it just converts the one-dimensional to two-dimensional convolutional. Okay. So, this is the same element-wise multiply and sum operation as a dot product, but applied to an matrix. That is what Hadamard product and summation. And dear friends, the kernel K here, yes, this exact kernel K determines what feature is detected. Let me just move on to this Gaussian smoothing kernel. A two-dimensional Gaussian kernel acts as a smoother. So here it replaces each pixel with a weighted average of its neighbor. So here, yeah, you can just specify as like g of x comma y, which equals e rise to the power of negative x square plus y square divided by sigma. Actually, dear friends, this one is what the exact functionality which we just specify mathematically as Gaussian smoothing kernel. And here kindly just one thing, this exact sigma controls the width, where if it is larger sigma, it just means more smoothing. So here we have actually creates a 21 into 21. So kindly just see here, 21 into 21 grid over the square of minus 3 comma 3 and minus 3 comma 3. And here this x grid and y grid stores coordinate for each kernel element. And kindly dear friends, this grid defines the spatial support of the kernel. And here next, of course, this is the exact one which provides the Gaussian kernel definition. So this is what the exact equation which we just got. So g of x comma y equals e raised to the power of negative x squared plus y squared divided by the sigma. And dear friends, this one is specified as a radially symmetric Gaussian-like function. And here, kindly just note a difference about this sigma. It is slightly different from the standard one. What is the exact standard one is e to the power of, that is raised x square plus y square divided by 2 sigma the square. Actually, this is what the standard one, and here we have slightly differed from the standard to make it radially symmetric Gaussian-like function. And again, I just specify this exact parameters, that is parameterized sigma. Okay, it is not a standard deviation. It is acts like a spread parameter. And next line, it is all about normalization. So kernel Gaussian. Okay, so this exactly ensures. So this exactly specifies as like a summation of ij of k sub ij, which is equal to 1. So actually why this matters is it just preserves overall image intensity. Actually, it is not about the brightness shift, okay? It just makes the kernel a proper average filtering. Okay, so this is what to make as a normalization. Okay, now let we just move on to this. Yeah, we are just going to diagonalize our kernel. So yes, we want to know what is the shape and what about the summation, whether after normalization, what is the exact value, and next about the peak. Okay, so what would be the central value also. Okay, so that is what we want to diagnose. So and we are just going to display it. And next, it just comes about generate a noisy image. And of course, you already know. So here we are just going to create an 100 into 100 Gaussian image. Okay, and each pixel is independent. And dear friends, high frequency content dominates. Next, we just going on smoothing. Okay, so this is what for convolutional smoothing, and yes, this is what it just interprets about the average functionality. So here, of course, what we just get is what I already specified, that is the output of I comma j, which is equal to summation of u and v and k of u comma v, and with the input of I minus u comma j minus v. Dear friends, this one, each pixel becomes a weighted average of its neighbor. So nearby pixel contributes more, mainly due to the Gaussian weight. Okay, so Gaussian weighting. And dear friends, here we have just specified mode is equal to same. Yes, here output which is equal to 100 and 100 comma 100. So it would be going to be the same as like the input size as 100 comma 100. And next one we have just done the boundary which is equal to wrap. So image wraps around edges. So that is what specified as like a periodic boundary. Okay, so next it is all about to visualize. So first of all, it is going to visualize an original image. So it is all about an random noise image. Okay, and next it is all about a Gaussian kernel. Okay, and kindly just to see here I just want to specify it is a original with appears as a high frequency noise, and next it is all about the Gaussian. So it just makes a brighter center and smoothness, okay, and smooth radially decay when it just goes outer, and represents spatial weighting also. So kindly just keep it in mind. And next we are just going to have the smoothened image. So in this, yes, noise is reduced, image appears blurred, blurred in the sense low pass filtered. Okay, so let me just execute and see the exact output. So kindly just see, dear friends. So observe here. So the Gaussian, so this is the exact original 100 into 100 image. Okay, and this one, it is all about the Gaussian kernel in 21 comma 21 matrix, where the bright center that faded towards the edges. Observe here. And here when convolute with a random noise image, the result is blurred version. And here high frequency pixel to pixel noise is averaged out. So leaving smooth low frequency patterns. Difference, the kernel is normalized, that is sums to 1. So the exact, see, kindly just see here, the kernel is normalized, that is sums to 1. So the convolutional computes a weighted average rather than a weighted sum. And this preserves the original intensity scale. And here I just want to specify one thing, dear friends. When you previously we have just seen about an 1D smoothing. Okay, 1D smoothing kernel where k is equal to 1 by m with all the values as like 1 the whole transpose. See, it was a uniform average. But here in the two-dimensional Gaussian kernel is a weighted average, whereby nearby pixels contribute more than the distant ones. So a more sophisticated version of a same idea. So here I just want to add one thing, dear friends, kindly just observe. Dear friends, whenever we just go on to this low pass filter, okay, so here high frequency variations are suppressed. So low frequency structure is preserved. And when going towards the local averaging, each pixel becomes weighted average of nearby. That is what I have just previously specified. And the third important thing about the sigma. Yes, the role of the sigma here, it is not a standard deviation. It just makes the spread parameter. And here I just want to specify, kindly just see here, if the sigma it is larger, so the exact kernel would be flattened and a blur would be stronger. And if the same sigma would be small, okay, so here the exact sharper would be the peak and blur would be reduced. That is, less blur would be there. Okay, and yes, the next I just want to specify about the convolutional as a linear operator. Dear friends, actually this exact operation, it is mainly used in linear functionalities and shift invariant, and of course equivalent to multiplication in the Fourier domain also. And one thing I have to specify, dear friends, whenever you just have, of course, I just give you in a pipeline. So whenever you just have this noise, yes, with a Gaussian convolutional, yes, you just get a smoothened signal. Okay, so a Gaussian kernel acts as like a probability distribution over the neighborhood. And here the convolutional performs a local expectation, that is weighted average. Okay, now let me just move on to the edge detection kernel. Dear friends, actually different kernels detect different feature. Actually here we are just going to construct a synthetic image with structured features and applies Sobel edge detection to extract intensity transition. And here kindly just observe this exact code demonstrate how convolutional kernels approximate spatial derivations. Okay, so yes, observe here, dear friends, here we are just going to have an initialize a blank grayscale image. Okay, so this is exactly a zeros. Okay, we are just going to create a blank grayscale image, and next we are just going to add a geometric shape. And here three regions with different intensity. Yes, one, it is all about bright square, and that is 1.0. Next, it is all about a medium rectangle, it is 0.7. And it's next it is dimension rectangle, it is of 0.5. So these introduced sharp edges, that is discontinuous. Okay, so now let me just add a horizontal gradient, and here it just adds a smooth left to right intensity increasing. So it just introduced a low frequency component. So kindly have a note on towards this. And yeah, here we are just going to include our Sobel edge detection kernel. And kindly observe, dear friends, we are going to have a horizontal Sobel detection. So this is what a horizontal Sobel detection of approximation of dou I by dou x. So it just responds strongly where intensity changes from left to right. And here it just comes the vertical. Okay, so this detects horizontal edges. Sobel horizontal, it just detects vertical edges, and Sobel vertical, it just detects the horizontal edges. Kindly just don't confusion with it. And it just approximate as dou I divided by dou y, and it just responds only for top to bottom changes. Now let me just apply the convolutional. So here we are just going to make the edge extraction, and this exactly applies discrete derivative filters. And observe, kindly see here, the mode is same. Okay, it just preserves the image size, and the boundary it's also as like fill, so it pads edges with 0. And yeah, here we have the gradient magnitude, and kindly just observe this exact gradient magnitude combines directional derivatives into a rotation invariant edge strength. Okay, so this exact gradient magnitude, let I just specify it mathematically. So actually it is a square root of horizontal edge the whole square plus vertical edges the whole square. So horizontal edges, yes, it is dou I by dou x the whole square plus dou I by dou y the whole square. So this is what the mathematical interpretation. So it just combines directional derivatives into a rotation invariant edge strength. Okay, now let me just have the visualization. So kindly just observe difference. This is how the visualization. And the first one, it is all about the original image. Yes, it just shows shapes and gradient. And here the displayed with color coding. Okay, so here we are just going to have the color coding as like positive versus negative weights. And yes, of course, here we are just going to have our annotations also, annotations numerically. And next, we are just going to have the bottom row, okay, as like vertical edges, horizontal edges, and edge magnitude. And dear friends, this vertical edges, it just highlights boundaries where intensity changes horizontally. And horizontal edges, of course, it detects top and bottom edge of the shapes. And last but not least, the edge magnitude, it just combines both fully edged map. Let me just visualize it. Okay, and here, dear friends, kindly just observe, we are just going to have the summation of that is kernel property zero sum. So here, when we just make the summation of this Sobel H and Sobel V, okay, we just get both equals to 0. So here I just want to specify the kernel property. So both it would be equal. That is when on mathematically interpreted, it is a summation of k sub ij which is equal to 0. So it ensures no response to constant region, only reacts to changes, not absolute intensity. Okay, so let me just see this by executing the code. And yeah, here we go. So this is what the top row, where we just get the original and Sobel horizontal and Sobel vertical. And towards the bottom row, yes, kindly just observe, these are the vertical edges of this virginal, and these are the horizontal edges of the virginal. And last but not least, it is all about the edge magnitude combining both vertical and horizontal. Difference, this edge detection, yes, of course, it is corresponds to high partial derivatives. And here Sobel filtering approximates gradient using finite differences. And if I just want to specify it with this value which we have just defined when on just making this mathematically, so kindly just observe, dear friends. Dear friends, actually this Sobel operator, we have 3 into 3 kernel that detects edges in specific orientation. One thing, horizontal orientation. And here, what is the exact horizontal orientation? Yes, so it is minus 1, 0, 1, minus 2, 0, 2, minus 1, 0, 1. So it exactly detects the vertical edges, and here changes in the horizontal direction. So it just goes for left to right, and of course the left to right asymmetry computes an approximation of dou I by dou x. And when on just going towards the vertical, so kindly just observe here when we just go for vertical Sobel. So here we have minus 1, minus 2, minus 1, and 0, 0, 0, and next it is all about 1, 2, 1. And this one detects the exact horizontal edges with approximation of dou I divided by dou y. And when coming with the edge magnitude, kindly just observe, when coming towards this edge magnitude, yes, we have the square root of edge horizontal, the whole square, plus edge vertical, the whole square. So combines both orientation, highlighting all edges regardless of this direction. Dear friends, both kernels sums to 0. Yes, that is what we just got. Both one, it sums to 0, which means they have no response in flat region. So add to the last, what we just have is larger the sum. That is, larger positive value appears on bright to dark transition, and larger negative values are dark to bright transition. So this is what both the things you have to keep it in mind. Okay, and this would be connected towards convolutional neural network. Yes, it just learns these kernels automatically from the data. The first layer of trained image classifiers typically discover this sober-like edge detector or Gabber-like orientation filter and color contrast filter. The same primitives used in classical computer vision but optimized for the task at hand. Okay, now let me just implement this by using a 2D convolutional here. Okay, so to reinforce the connection of this dot product filtering, we implement the double loop explicitly. Okay, so that is what we are just going to do here. Kindly just observe, dear friends. So this exact code actually implements 2D convolutional. Okay, so using a sliding window and verifies it according against this SkyPy cross correlation. And of course, dear friends, it explicitly exposes the mechanism behind convolutional as a sequence of which I have already specified. Yes, Hadamard, that is element-wise products plus summation. Okay, that is what we are just going to do. So let me just first define the function. This exact function, it just gives the convolutional 2D, and here we have the parameter as like image and kernel. Okay, and here this two are the inputs, where image, it has a 2D height and width array, and here this kernel, it is as like a 2D filter. And what would be the output is, yeah, we are just going to have a filtered image of the same size. Kindly keep it in mind. Okay, and in this we are just going to have our kernel geometry. Okay, so here we have the kernel geometry. It just determines the kernel size and its center offset, and it just assumes odd sized kernel, that is as like 3 into 3 matrix or 3 into 3 Sobel, like that. Okay, and let me just have our image padding, and dear friends, this enables applying the kernel at border pixel, and it just uses the 0 padding, which is equivalent to which we have already specified na boundary, which is equal to fill. Okay, now next we are just going to have a sliding window computation. So this sliding window computation, it just has to extract a local patch and element-wise multiple, and next is summation. So this is what the exact one we are expecting. So what it is, I just let you know. The first one, it is all about local patching is extracted. So the patch which would be got from the row wise and column wise. And next one, it is all about element wise multiple. Element wise multiple, yes, it patch dot matrix with the kernel. And next, it is all about the summation. The summation, yes, we are just going to have the summation of ij, that is patch of ij and kernel sub ij. And yes, this is what the exactly which we are just going to have as like image into kernel with row and column. Okay, so row comma column. Okay, dear friends, let me just have the next one. It is what the cross correlation one. Okay, so that is what here we are making it with a flipped functionality. Cross correlations versus convolutional. So here cross correlation, we are just going to calculate it by correlated 2D, and convolutional by using this convolutional 2D manually. Okay, and here this convolutional 2D, it just flips the kernel, and correlated 2D, yes, it does not flip it. Okay, so yes, let me just validate it by using this results SkyPy by this correlated 2D, and we all just think we are going to have our output. And let me just check what is the conforms the numerical evaluation. So once I execute, let me just give what it is. Yeah, here we go. And kindly just to see here, dear friends, the output here, we have the shape, of course, we already know 100 to 100, and the kernel shape, yeah, it is 3 into 3. Okay, and output, it is the same as like the input images. And here kindly just observe whether it is matches. Of course both are matching, so it is true. And next, it all gives the near machine precision. So this is what the maximum difference. And actually see here difference when we just have this implementation. Okay, so the manual implementation confirms that 2D convolutional is exactly what we described. At each position, extract a patch the same size as a kernel, compute the Hadamard product. Okay, so that is what here it is provided. And next, it just makes the summation. Okay, so here that is what. But when coming towards this convolutional output, so formally convolutional flips the kernel before sliding. So cross correlation does not. For symmetric kernel like this Gaussian, they are identical. And of course, I want to add one thing. For asymmetric kernels like Sobel, the sign can differ. Okay, so here of course I have to specify, as I have already previously specified, that we have applied with an double loop. So yes, this exact double loop we just have it towards the big O method of NR into NC and to the same KR into KC. For this, if we just have as 1000 into 1000 an image with a 21 into 21 kernel, okay, so this is image and this is a kernel, and that is approximately what we just get is approximately 4.1 into 10 to the power of 8 operations. So this, the convolutional theorem offers a faster path convolutional in a spatial domain that equals multiplications in the frequency domain, that reducing the complexity of this we can go via using this FFT. Okay, so that is what the difference. Okay, so let me just move on to the next one. Yes, we are going to have the effect of Gaussian width. Difference previously I have just specified about the parameter sigma. Yes, this exact code, it just illustrates how this parameter sigma here controlling the spread of a Gaussian kernel that affects the strength of the image smoothing. So it applies Gaussian filtering with increasing spread to a noisy image and compares the result. Okay, so let me just make it. And here as of course dear friends, we are just going to generate an 80 into 80 image of independent Gaussian noise. So that contains predominantly high frequency component. And here we have our sigma value. Okay, so 2, 10, 40. So these controls the spread of Gaussian kernel. So larger value, border kernel, strong smoothing. Kindly keep it in mind. Okay, now let me just go with the Gaussian kernel construction. Okay, so here this exact Gaussian kernel constructions as per the sigma value. And here I have already specified previously. Anyhow, I just remind you again. So yes, k of x comma y, which is equal to expression that is raised to minus x square plus y square divided by sigma. And here it just defines on of course 15 into 15 fixed grid. Okay, and here it is normalized to sum of k, which is equal to 1. Okay, so that is what here it is specified. Okay, now let me just go for smoothing. And here, when on just making this smoothing, that is applies this Gaussian smoothing, each pixel becomes a weighted average of the neighbor. And here we have the boundary as wrap. So it treats the image as periodic, that is edges wraps around. And let me just have this as an visualization output. So here we have the panel 1, so original noise, and other 3, that is from 2 to 4, we are just going to have the smoothened results of increasing this sigma, that is 2, 10 and 40. Let me just see here. Okay, so let I execute and we observe the value of sigma is small. The kernel is sharply peaked, and here only nearby pixel contributes. So here slightly smoothened, but noise still prominent. Okay, next let me just go for sigma, which is 10. Of course it is moderate, so kernel spreads out, and here more neighbors contribute. And what was the resultant? Of course, noticeably there is a blur is there, noise reduced, but emerging smooth structure emerging here, and all that. Okay, last but not least, the sigma, which is equal to 40. Yes, kernel becomes very flat and large neighborhood average. So here it has resulted with a smooth, strong smoothening and image approach low frequency field. So fine detail completely removed. Difference here, I want to specify an important functionality. Whenever we just go for this sigma functionalities, as here, sigma increases, the Gaussian kernel becomes wider, that is flatter, averaging over a large neighborhood. So the effect progresses from light denoising to aggressive blurring. Okay, so that reveals only the coset structure. And here I have already specified one thing, dear friends. We have used the exact kernel we have used as like the expression minus x square plus y square divided by sigma. But there is a standard one. Yes, the standard one is the expression raised to minus x square plus y square divided by 2 sigma the square. So this is the exact one. So here this sigma is not a statistical standard deviation. It is still monotonically controlled smoothening strength. And here we have a fixed kernel size as like 15 into 15. We have already specified that. And this implication, yes, the very large sigma, yes, here the Gaussian is truncated, kernel becomes nearly uniform within the window. So true large sigma behavior would require a large kernel support. So for that we have just used this. Okay, and dear friends, yes, by practicing, yes, the choice of this sigma depends on the application. When you just go towards anything as like image denoising, so here the small sigma would preserve the details. Okay, and if you just go for anything as like an background estimation, so here large sigma to capture border trends. So kindly make use of a larger sigma. And if it is a scale or space analysis, here we just need multiple sigma values simultaneously to detect features at a different scale used in SIFT or any other key detectors. Okay, so yes, dear friends, so I think in this session we have discussed about the convolutional functionalities, that is image filtering, that extended from this one-dimensional to two-dimensional functionalities by using this Hadamard product and the summation, that sliding 2D kernels. And here Gaussian kernel smooths images, Sobel kernels detect edges, and the kernel's shape determines what feature is detected. And here modern CNN learns optimal kernels through gradient descent. So dear friends, we can from this whole the session we have understood that matrix operations are organized collection of dot product and norms. And here we have just discussed about the covariance. So the exact covariant matrix is a matrix of dot product, and convolutional is a matrix of local dot product. And when coming towards the transformation, yes, is a matrix encoding a specific rotation or scaling applied via that dot product. So linear algebra becomes more powerful as we scale from vectors to matrices, but the foundation remains the same. Hope this session would be very useful for you. And kindly just like this video, share it with someone starting with their AI journey. Okay, dear friends, thanks for watching and see you in the next session.